Hello, and welcome to a journey into the unknown. This is your invitation to drift away from the familiar shores of what we think we know and venture into the deepest mysteries our planet has to offer. Tonight, we're diving into something that covers more than 70% of Earth's surface, yet remains more alien to us than the surface of Mars: the ocean. That vast, dark expanse that has cradled life for billions of years, shaped our climate, and continues to hide secrets in its depths that would fundamentally change how we see our world. Before we begin this exploration, I'd love to know where you are listening from, perhaps near a coastline or thousands of miles inland. And if you enjoy these deep dives into the unknown, a like and subscribe would mean the world to me. And don't worry, I'll try my best not to make this so fascinating that you lose sleep pondering the mysteries below, though if you do, at least you'll drift off having learned something extraordinary along the way. So let's begin with a question that should stop you in your tracks. If I told you that we've explored less than 5% of our oceans, would you believe me? If I told you that we have better maps of the surface of Venus, a planet shrouded in crushing toxic clouds and temperatures hot enough to melt lead, than we do of our own ocean floor, would that surprise you? And if I told you that there are entire mountain ranges, deeper than the Grand Canyon, teeming with life forms that seem to belong in science fiction, all hiding beneath the waves just miles from where you might have gone swimming last summer, would you think I was exaggerating? I'm not. The ocean is Earth's final frontier, a realm so vast and unexplored that every expedition into its depths reveals wonders that challenge our understanding of life itself. We've sent humans to the moon, rovers to Mars, and telescopes to the edge of the observable universe. Yet the deepest parts of our own planet remain as mysterious as the day the first humans gazed out at the endless blue horizon. Tonight, we're going to uncover why this is the case, what we've discovered in the tiny fraction we have explored, and what mind bending secrets might be waiting in the darkness below. This isn't just a story about water and marine life. This is a story about the limits of human knowledge, the incredible resilience of life, and the humbling reality that our own planet still holds mysteries that could rewrite the textbooks. But here's what makes this even more remarkable. The ocean isn't just some distant, unreachable frontier like deep space. It's right here covering most of our world, influencing every weather pattern, every breath of air, every drop of rain that falls. Yet it remains largely unknown to us, a testament to just how challenging it is to explore a realm where the pressure can crush submarines like tin cans and where sunlight has never penetrated. Let me paint you a picture of just how little we know. Imagine if you were trying to understand all of human civilization, but you were only allowed to examine 5 city blocks out of every 1,000 that exist. That's essentially where we stand with ocean exploration. We've mapped the entire surface of the moon in stunning detail. We've photographed distant galaxies billions of light years away, yet vast portions of our ocean floor remain as unmapped and unknown as they were to the ancient mariners who feared sailing off the edge of the world. The numbers alone are staggering. Our oceans contain 99% of the living space on Earth. Let that sink in for a moment. Nearly all the room for life on our planet exists beneath the waves, in a three-dimensional realm that stretches from the sunlit surface to crushing depths that would make the peak of Mount Everest seem like a gentle hill by comparison. And yet, we've explored such a tiny fraction of this space that calling it the tip of the iceberg would be generous. But why is this the case? What makes the ocean so much more challenging to explore than the vacuum of space or the surface of other planets? The answer lies in one of the most fundamental forces in the universe: pressure. And when I say pressure, I'm not talking about the gentle squeeze you might feel diving to the bottom of a swimming pool. I'm talking about pressure so intense it would instantly crush a human body. Pressure that increases relentlessly with every meter of depth. Pressure that makes the engineering challenges of space exploration look almost simple by comparison. Consider this. When you're standing at sea level, the entire weight of Earth's atmosphere presses down on you at about 14.5 pounds per square inch. Your body is perfectly adapted to this pressure, so you don't even notice it. But descend just 10 meters beneath the ocean's surface, and that pressure doubles. Go down another 10 meters, and it doubles again. By the time you reach the deepest parts of the ocean, the pressure is more than 1,000 times greater than what you're experiencing right now. It's equivalent to having about 50 jumbo jets stacked on top of every square meter of your body. This crushing pressure creates engineering challenges that make rocket science look straightforward. A spacecraft needs to keep one atmosphere of pressure in while keeping the vacuum of space out. But a deep sea submersible needs to protect its human occupants from pressures that would implode most materials in milliseconds. The walls of deep sea vehicles aren't just thick, they're marvels of engineering, crafted from specialized alloys and designed with mathematical precision to withstand forces that few things on Earth ever encounter. And pressure is just the beginning of the challenges. The ocean is vast beyond comprehension, covering more than 360 million square kilometers of Earth's surface. If you were to drain all the water from the oceans, you'd reveal a landscape more alien and dramatic than anything science fiction has ever imagined. Underwater mountain ranges that dwarf the Himalayas, canyons that make the Grand Canyon look like a crack in the sidewalk, and volcanic vents that spew superheated water into the abyss, creating oases of life in the most unlikely places. The deepest part of the ocean, the Mariana Trench in the Pacific, plunges down more than 11 kilometers below sea level. If you could somehow place Mount Everest at the bottom of this trench, its peak would still be more than 2 kilometers underwater. And this isn't some narrow crack in the Earth's surface. The Mariana Trench is part of a vast underwater landscape of ridges, valleys, and plains that we've barely begun to map, let alone explore. But perhaps the most humbling aspect of our ocean ignorance is how recently we've made even our most basic discoveries about the deep sea. The mid-ocean ridges, underwater mountain chains that form the longest mountain range on Earth, weren't even discovered until the 1950s. These ridges stretch for more than 65,000 kilometers around the globe, making them longer than all the mountain ranges on land combined, yet they remained completely unknown to science for most of human history. And it's not just the geography that's mysterious. The life forms that exist in the deep ocean are so bizarre, so perfectly adapted to extreme conditions, that they challenge our very understanding of what life can be. In the crushing darkness of the deep sea, creatures have evolved that would seem impossible if we hadn't seen them with our own eyes. Fish with transparent heads, jellyfish the size of dinner plates that glow with their own light, and octopi that live at depths where the pressure would instantly kill most surface dwelling creatures. Some of these deep sea organisms have been alive for centuries, growing slowly in the cold darkness, outliving entire human civilizations. There are deep sea corals that were already ancient when Shakespeare was writing his plays, still growing, still thriving in conditions that would be instantly fatal to almost any surface life. And we're only just beginning to discover them. The technology required to explore these depths is so specialized, so expensive, and so challenging to operate that only a handful of vehicles in the world are capable of reaching the deepest parts of the ocean. More people have been to space than have visited the deepest point on Earth. The Challenger Deep, the lowest known point in the ocean, has been visited by fewer people than have walked on the moon. And unlike space missions, which can be controlled remotely from millions of kilometers away, deep sea exploration requires vehicles that can operate autonomously in an environment where communication with the surface is nearly impossible. Radio waves, which work perfectly in the vacuum of space, are completely useless underwater. Sound travels better in water than in air, but even sound waves are limited in the deep ocean. The result is that deep sea explorers often work in isolation, cut off from the surface world, relying entirely on their training and their equipment to survive in an environment more hostile than outer space. And yet, every time we do manage to send a camera or a submersible to unexplored depths, we discover something that expands our understanding of life on Earth. New species are discovered with almost every deep sea expedition, not just variations on known creatures, but entirely new forms of life that have evolved in isolation for millions of years, developing survival strategies so unique that they're forcing scientists to rewrite the rules of biology. The ocean's role in shaping our planet's climate is equally mysterious and equally important. The ocean acts as a massive heat engine, absorbing solar energy at the equator and distributing it around the globe through currents that flow like rivers beneath the waves. These currents, some of which carry more water than all the rivers on land combined, determine weather patterns, influence the formation of storms, and even affect the timing of ice ages. But our understanding of these currents, particularly the deep ocean currents that flow along the ocean floor, remains incomplete. We know they exist. We know they're crucial to our planet's climate system, but we don't fully understand how they work or how they might change as our planet warms. Climate models rely heavily on assumptions about ocean behavior, assumptions that are difficult to verify because so much of the ocean remains unexplored. This brings us to one of the most sobering aspects of our ocean ignorance. We're changing something we don't fully understand. Human activities are altering ocean chemistry, ocean temperature, and ocean currents faster than we can study them. We're conducting a global experiment with a system so complex and so poorly understood that we can't predict the outcomes with confidence. The ocean absorbs about a quarter of all the carbon dioxide we pump into the atmosphere, making it a crucial buffer against climate change. But this absorption comes at a cost. As carbon dioxide dissolves in seawater, it makes the ocean more acidic, a process that's happening faster today than at any time in the past 300 million years. The implications of this acidification are still being studied, but early signs suggest it could have profound effects on marine life, particularly creatures that build shells or skeletons from calcium carbonate. And this is happening in an ocean we've barely explored. We're changing the chemistry of a realm that's home to the vast majority of life on Earth, yet we don't even know what most of that life looks like. Every species that goes extinct before we discover it takes with it millions of years of evolutionary innovation, unique solutions to the challenges of survival that we'll never have the chance to understand or learn from. The pace of ocean exploration has accelerated dramatically in recent decades, driven by advances in technology and growing awareness of how much we don't know. Robotic submersibles can now reach depths that were impossible to explore just a few decades ago, and satellite technology allows us to map ocean currents and temperatures on a global scale. But even with these advances, the ocean remains largely unexplored, a frontier so vast that it will likely take centuries to map and understand completely. Every expedition into the deep reveals just how much we still don't understand about the very foundation of life on our planet. Consider the discovery of hydrothermal vents in 1977, a finding so revolutionary that it fundamentally changed our understanding of how life can exist. Before this discovery, scientists believed that all life on Earth ultimately depended on energy from the sun. Photosynthesis was considered the foundation of every food chain, the process that converted sunlight into the chemical energy that powered all living things. But at the bottom of the ocean, in complete darkness, where no sunlight has ever penetrated, researchers found thriving ecosystems built around volcanic vents spewing superheated, chemical rich water into the abyss. These weren't just a few hardy bacteria clinging to life in impossible conditions. These were complex communities of creatures, from giant tube worms, longer than baseball bats, to ghostly white crabs and bizarre fish species that had never been seen before. See, the tube worms were particularly astonishing. They had no mouth, no stomach, no digestive system as we understood it. Instead, they housed billions of bacteria within their bodies, bacteria that could take the toxic chemicals pouring from the vents and convert them directly into food. It was an entirely different way of creating energy for life, a process called chemosynthesis that didn't require sunlight at all. This discovery didn't just add a few new species to the catalog of known life. It opened up entirely new possibilities for where life might exist, not just on Earth, but throughout the universe. If life could thrive around volcanic vents on the ocean floor, perhaps it could exist in the subsurface oceans of Jupiter's moon Europa, or beneath the frozen surface of Saturn's moon Enceladus. The deep ocean had revealed that life was far more adaptable and resourceful than we had ever imagined, and we're still discovering new hydrothermal vent fields regularly. Each one hosts its own unique community of creatures, many of which exist nowhere else on Earth. These isolated populations have been evolving separately for millions of years, creating a kind of biological laboratory where evolution has been experimenting with different solutions to the same basic challenge. how to survive in one of the most extreme environments on the planet. The creatures living around these vents face challenges that would instantly kill most surface life. The water temperature can exceed 400 degrees Celsius, hot enough to melt lead, yet just meters away the water is barely above freezing. The chemical composition of the vent water is so toxic it would dissolve human tissue in minutes. The pressure is crushing, the environment is completely dark, and there's no oxygen in the traditional sense that most life requires. Yet not only do creatures survive in this environment, they flourish. Some of the biomass concentrations around hydrothermal vents rival those found in tropical rainforests, creating oases of life in what was once thought to be a biological desert. The giant tube worms can live for centuries, growing slowly but steadily in the perpetual darkness, creating communities that persist for generations in conditions that seem incompatible with complex life. But hydrothermal vents represent just one type of extreme environment in the deep ocean. There are cold seeps where methane and hydrogen sulfide leak from the seafloor, creating different but equally remarkable ecosystems. There are underwater lakes of brine so dense that submarines can actually float on their surface, creating the surreal sight of a lake at the bottom of the ocean. There are deep sea mountains where currents create upwelling zones that support unique communities of filter feeding creatures, and abyssal plains where life exists in conditions of perpetual food scarcity, colds, and darkness. Each of these environments has produced its own evolutionary solutions, its own catalog of impossible creatures. There are fish that produce their own light through chemical reactions, creating living lanterns in the darkness. There are predators with jaws that can unhinge to swallow prey larger than themselves, an adaptation to the scarcity of food in the deep ocean where every meal might be your last for months. There are creatures so bizarre that when they're first discovered, scientists struggle to understand what they're looking at. The barrel-eye fish has a completely transparent head, allowing its tubular eyes to rotate upward to spot the silhouettes of prey against the faint light filtering down from above. The vampire squid can turn itself inside out when threatened, revealing spines that make it look like something from a nightmare. The anglerfish uses a bioluminescent lure to attract prey in the darkness, but some species take this strategy to an extreme where the tiny male permanently fuses to the much larger female, becoming essentially a living reproductive organ. These aren't just curiosities or evolutionary oddities. Each of these creatures represents millions of years of adaptation to extreme conditions, and studying them is providing insights that could revolutionize medicine, materials, science, and our understanding of the limits of life itself. The proteins that allow deep sea creatures to function under crushing pressure could lead to new industrial applications. The bioluminescent chemicals that create living light in the darkness are already being used in medical research and biotechnology. But perhaps most remarkably, we're discovering that the deep ocean plays a much more active role in global processes than we ever realized. The seafloor isn't just a passive repository for sediments and debris from the surface. It's a dynamic, living system that actively processes chemicals, cycles nutrients, and influences ocean chemistry on a global scale. Microorganisms living in seafloor sediments, sometimes kilometers below the ocean floor itself, are slowly but continuously processing organic matter, releasing chemicals that affect ocean chemistry and potentially even influencing global climate patterns. These deep subsurface communities might represent the largest ecosystem on Earth, containing more biomass than all terrestrial life combined, yet we've only just begun to study them. The discovery of these subsurface communities has profound implications for our understanding of life's limits. If microorganisms can thrive kilometers beneath the seafloor, in sediments that are millions of years old, it suggests that life might be possible in environments we never considered habitable. The deep subsurface of Earth might contain a shadow biosphere, an entire realm of life that operates on timescales and in conditions completely different from the surface world we know. These organisms live their entire lives in darkness, feeding on chemical energy and organic matter that settled to the seafloor eons ago. They reproduce incredibly slowly, with some individuals possibly living for thousands of years. They represent a completely different approach to existence, one based not on rapid growth and reproduction, but on incredibly efficient use of limited resources and extraordinary longevity. The implications extend far beyond Earth. If life can exist in such extreme conditions, thriving kilometers beneath the surface in environments cut off from sunlight and fresh nutrients for millions of years, then the possibilities for life elsewhere in the universe expand dramatically. The subsurface oceans of icy moons suddenly seem much more promising as potential habitats, and the definition of habitable zones around other stars might need to be reconsidered. But studying these deep subsurface communities presents challenges that make exploring the deep ocean look straightforward by comparison. Drilling into seafloor sediments requires specialized equipment and techniques, and contamination is a constant concern. How do you distinguish between indigenous microorganisms that have lived in the sediments for millions of years and contamination introduced during the drilling process? How do you study organisms that live and reproduce so slowly that laboratory experiments might take decades to yield results? The technological challenges of deep ocean exploration continue to push the boundaries of engineering and materials science. The pressure vessels required to protect instruments at great depths must be incredibly precise. A tiny flaw in the design or construction could result in catastrophic implosion, destroying not just expensive equipment, but potentially taking lives. The materials used must maintain their strength and flexibility under conditions that would cause most substances to become brittle and fail. Communication with deep sea vehicles remains one of the most significant technical challenges. While spacecraft can maintain constant radio contact with Earth across millions of kilometers of vacuum, a submersible just a few kilometers beneath the ocean surface might as well be on another planet when it comes to communication. Sound waves can travel through water, but they're slow and can be distorted by temperature layers and ocean currents. This means that deep sea exploration often requires vehicles that can operate autonomously for hours or days, making critical decisions without human input. The development of new exploration technologies is accelerating, driven by advances in materials, science, robotics, and artificial intelligence. Autonomous underwater vehicles are becoming more sophisticated, capable of making complex decisions about where to explore and what to investigate. Advanced sonar systems are providing increasingly detailed maps of the seafloor, revealing features that were previously invisible. But even with these advances, the scale of the unexplored ocean remains daunting. The Pacific Ocean alone covers more area than all the continents combined, and its average depth is over 4 kilometers. Exploring it systematically would require resources and time commitments that dwarf current ocean research budgets. The entire global deep sea research fleet consists of just a handful of vehicles capable of reaching the greatest depths, and each expedition represents a massive investment in time, money, and human expertise. This scarcity of exploration resources means that every deep sea expedition must be carefully planned to maximize scientific return. Researchers can't simply decide to explore a particular area on a whim. They must compete for limited time on specialized vessels, justify their research proposals, and often wait years for an opportunity to visit their study sites. The result is that our knowledge of the deep ocean remains fragmentary, based on brief visits to scattered locations rather than comprehensive surveys. It's as if we were trying to understand terrestrial ecosystems based on a few hours spent in random locations around the world, with years between each visit. We might discover a rainforest in one location and a desert in another, but we'd have no understanding of how these ecosystems connect, how they influence each other, or what lies between them. This fragmented knowledge becomes even more problematic when we consider how rapidly human activities are changing the ocean. Deep sea mining operations are beginning to extract minerals from the seafloor, potentially disrupting ecosystems we haven't even discovered yet. Pollution from the surface world is reaching even the deepest ocean trenches, with plastic debris and industrial chemicals found in creatures living at depths previously thought to be completely isolated from human influence. Climate change is altering ocean temperatures, chemistry, and circulation patterns faster than we can study them. The deep ocean, which was once considered stable and unchanging, is now recognized as dynamic and responsive to global changes. But our ability to monitor and understand these changes is limited by our fundamental lack of knowledge about baseline conditions in most of the ocean. We're essentially trying to detect changes in a system we don't fully understand, using measurements from locations we can rarely visit. It's like trying to diagnose changes in a patient's health when you've only examined a tiny fraction of their body and have no baseline measurements for comparison. The challenges become even more stark when we consider what we call the twilight zone of the ocean, that vast middle layer between the sunlit surface waters and the crushing depths below. This zone, stretching roughly from 200 to 1,000 meters beneath the surface, might contain more life than all other ocean zones combined, yet it remains almost completely unexplored. During the day, this twilight zone appears relatively empty to our instruments, but as darkness falls on the surface, something extraordinary happens. The largest migration on Earth begins, a nightly journey involving billions upon billions of creatures raking from the depths toward the surface to feed, then descending again before dawn. This migration is so massive that early sonar operators during World War II thought they had discovered a false seafloor, a solid layer that appeared to rise and fall with the rhythm of day and night. We now know this deep scattering layer consists of countless small fish, squid, jellyfish, and crustaceans, making their daily vertical journey. But the scale of this migration defies comprehension. The biomass involved might exceed that of all terrestrial animals combined, yet we can barely begin to catalog what's participating in this ancient rhythm, let alone understand why it evolved or how it affects global ocean processes. What makes this migration even more mysterious is that many of the creatures involved remain completely unknown to science. They live their entire lives in the twilight zone, coming close enough to the surface each night that we can detect their presence, but remaining too deep and too scattered for comprehensive study. Each time researchers do manage to sample this zone, they discover new species, new behaviors, new biological strategies that challenge our understanding of marine ecosystems. The economic implications of our ocean ignorance are staggering and largely unrecognized. The ocean provides services to human civilization that are difficult to quantify but absolutely essential. It regulates our planet's temperature, produces more than half the oxygen we breathe, and provides the primary protein source for over 3 billion people. Yet we're managing these resources based on incomplete information, making decisions about fishing quotas, shipping routes, and industrial development without understanding the full consequences. Consider the simple question of how many fish are in the ocean. It seems like basic information we should have, but the truth is we have no reliable global estimates for most species. Our fisheries models are based on catches and population surveys from a tiny fraction of ocean habitats, primarily those close to shore and accessible to fishing vessels. The vast majority of ocean fish populations remain uncounted and unstudied. This knowledge gap becomes critical when we consider that many commercial fish species spend parts of their life cycles in deep water or remote ocean areas we rarely visit. We might be managing surface populations while remaining completely ignorant of the deep water nurseries or spawning grounds that sustain them. It's like trying to manage a forest by only counting the trees visible from a single hiking trail. The pharmaceutical potential of deep sea organisms represents another dimension of our lost opportunities. Many of the creatures living in extreme ocean environments produce chemical compounds unlike anything found on land or in shallow water. These compounds, evolved over millions of years to function under crushing pressure in toxic environments or in complete darkness, often have properties that could revolutionize medicine. Already, the few deep sea organisms we have studied have yielded compounds with anti cancer properties, powerful antibiotics, and molecules that could treat neurological disorders. But for every deep sea species we've analyzed, thousands more remain undiscovered. Each extinction, each habitat destroyed before we can study it, potentially eliminates solutions to medical problems that plague humanity. The tragedy is that we're losing these opportunities at an accelerating pace. Deep sea mining operations are beginning to scrape the seafloor for metals needed in renewable energy technologies, potentially destroying ecosystems before we even know they exist. The irony is profound. In our rush to develop technologies to address climate change, we might be eliminating the very biological resources that could help us adapt to the changes already underway. Ocean acidification, the result of increased carbon dioxide absorption, is already altering marine chemistry faster than most organisms can adapt. But we don't know which species are most vulnerable because we don't know what most deep sea species are or how they live. We're conducting a global chemistry experiment while remaining ignorant of most of the participants. The temperature changes associated with climate change are perhaps even more concerning. The deep ocean, which has remained stable for millions of years, is beginning to warm. Deep water currents that have flowed unchanged since the end of the last ice age are starting to shift. But our understanding of these currents is so limited that we can't predict where they're going or what the consequences might be. These deep currents don't just move water, they move nutrients, oxygen, and heat around the globe. They influence weather patterns on every continent and determine the productivity of marine ecosystems worldwide. If they change significantly, the effects could dwarf anything in recorded human history. Yet we're monitoring these changes with a network of instruments so sparse that entire ocean basins have only a handful of measurement stations. The technological solutions to ocean exploration are advancing rapidly, but they're still inadequate to the scale of the challenge. Autonomous underwater vehicles are becoming more sophisticated and less expensive, but they're still limited by battery life, communication challenges, and the sheer vastness of the areas they need to cover. A state of the art robotic submarine might operate for 24 hours and cover a few dozen square kilometers before needing to return to the surface. To put this in perspective, exploring just the Pacific Ocean at the resolution we've achieved for land would require millions of such missions. Even with dramatic improvements in technology and massive increases in funding, comprehensive ocean exploration would take centuries. And that's assuming the ocean remains stable while we study it, which is increasingly unlikely given the pace of global change. Satellite technology has revolutionized our ability to study the ocean surface, providing global measurements of temperature, currents, and biological productivity. But satellites can only penetrate a few meters into the water column. Everything below that thin surface layer remains as mysterious as it was to ancient mariners. It's as if we were trying to understand a skyscraper by only examining its roof. The biological discoveries emerging from the small fraction of deep ocean we have explored continue to challenge our most basic assumptions about life. We've found organisms that seem to violate the rules of biochemistry, thriving in conditions that should be instantly lethal. There are bacteria that can survive temperatures that would sterilize medical instruments, and complex animals that can withstand pressure changes that would explode human cells. Some deep sea creatures have evolved solutions to survival that seem almost magical. There are fish with antifreeze proteins in their blood that prevent ice crystal formation at depths where the water is below the normal freezing point of body fluids. There are organisms that can slow their metabolism to almost nothing during periods of food scarcity, essentially putting themselves into suspended animation for months or years. Perhaps most remarkably, we've discovered that many deep sea organisms have lifespans that dwarf those of terrestrial creatures. Some deep sea corals are thousands of years old, growing slowly in the cold darkness, accumulating centuries of environmental information in their skeletons. These organisms were already ancient when human civilization began, and they're still growing today, living libraries of ocean history that we're only beginning to learn how to read. The genetic diversity hidden in the deep ocean likely exceeds that of all terrestrial ecosystems combined. Each isolated population, each unique environment, has served as a laboratory for evolution, producing solutions to survival challenges that exist nowhere else on Earth. This genetic library contains information accumulated over hundreds of millions of years of evolution, representing biological innovations that could transform biotechnology, medicine, and materials science. But this diversity is also incredibly fragile. Many deep sea species have small populations restricted to specific habitats. A single mining operation or pollution event could eliminate entire species before we even know they exist. Unlike terrestrial extinction, where we usually have some record of what we've lost, deep sea extinctions might occur without any human awareness that something unique has vanished forever. The interconnectedness of ocean systems means that changes in one area can have cascading effects across entire ocean basins. Deep currents connect the polar regions to the tropics, carrying nutrients, heat, and organisms across thousands of kilometers. A change in deep water formation in the Arctic can affect upwelling patterns near the equator, influencing marine productivity in regions that seem completely unrelated. These connections operate on timescales that challenge human understanding. Water that sinks in the North Atlantic might not return to the surface for hundreds of years, carrying with it the chemical signature of the atmosphere from when it last saw sunlight. The deep ocean contains a record of past climate conditions, stored in water masses that have been isolated from the surface for centuries. Understanding these connections requires a global perspective that current research infrastructure can't provide. We need simultaneous measurements from all ocean basins, coordinated studies that track water masses and their properties as they move around the globe, and long-term monitoring programs that can detect changes occurring over decades or centuries. The deep ocean also plays a crucial role in regulating Earth's carbon cycle, absorbing vast quantities of carbon dioxide from the atmosphere and storing it in deep water masses and seafloor sediments. But this carbon storage isn't permanent. Changes in ocean circulation or chemistry could release stored carbon back to the atmosphere, potentially accelerating climate change in ways that current models don't fully account for. We're already seeing hints that this process might be beginning. Ocean temperatures are rising, ocean chemistry is changing, and circulation patterns are shifting. But our understanding of these systems is so limited that we can't predict whether the ocean will continue to act as a carbon sink or might become a carbon source, amplifying rather than moderating climate change. The scale of our ignorance about ocean carbon storage is particularly troubling because it represents one of the largest uncertainties in climate science. The ocean contains roughly 50 times more carbon than the atmosphere, stored in various forms throughout the water column and in seafloor sediments. Small changes in how this carbon is cycled could have enormous effects on atmospheric carbon dioxide levels and global climate. Yet we're making critical decisions about carbon emissions and climate policy without understanding how the ocean carbon system works or how it might respond to continued changes. It's like trying to balance a checkbook when you don't know the balance in your largest account and can't predict how much interest it might earn or lose. The deep ocean's role in oxygen production and distribution is equally mysterious and equally important. While most people know that marine phytoplankton produce much of the oxygen we breathe, fewer realize that the distribution of this oxygen throughout the ocean depends on deep currents and mixing processes we barely understand. Large areas of the deep ocean are naturally low in oxygen, creating zones where only specially adapted organisms can survive. But these oxygen minimum zones are expanding as ocean temperatures rise and circulation patterns change. If this expansion continues, it could dramatically alter marine ecosystems and reduce the ocean's overall productivity. The implications extend beyond marine life to human societies that depend on ocean resources. Fisheries could collapse, coastal communities could face unprecedented challenges, and the ocean's ability to moderate climate change could be compromised. Yet we're monitoring these changes with instruments so sparse and measurements so infrequent that we might not recognize critical tipping points until after we've passed them. Perhaps most humbling of all is the realization that our ignorance about the ocean extends to its most basic properties. We don't know how much water the ocean contains, how deep it is on average, or how its volume changes over time. These seem like fundamental questions with straightforward answers, but the ocean is so vast and so difficult to measure that even these basic facts remain uncertain. Sea level measurements, crucial for understanding climate change impacts, are complicated by the fact that the ocean surface isn't actually level. Gravitational anomalies, wind patterns, and current systems create hills and valleys in the ocean surface that can be several meters high. Measuring absolute sea level requires understanding these variations, but mapping them globally requires satellite measurements so precise that tiny errors in our understanding of Earth's gravitational field can throw off the calculations. The ocean continues to humble human knowledge and technical capabilities, reminding us that despite all our technological advances, we remain newcomers to a planet that has been shaped by forces operating on scales of time and space that challenge our comprehension. Every expedition into the deep reveals not just new discoveries, but new questions, new mysteries, and new appreciation for the complexity of the systems that sustain life on Earth. In the darkness below, in pressures that would crush our bodies and temperatures that would freeze our blood, life continues its ancient dance of adaptation and survival. Creatures we've never seen are solving problems we've never considered, using strategies we've never imagined, in an environment more alien than the surface of Mars, yet more crucial to our survival than the air we breathe. The ocean remains Earth's greatest frontier, a realm of mystery that spans our entire planet, influences every aspect of our climate and weather, and contains the vast majority of life on Earth. Yet we've explored so little of it that we can't even estimate what we don't know. Every drop of seawater contains mysteries. Every cubic meter of ocean hides secrets, and every expedition into the depths reveals how much more there is to discover. We stand at the shore of an ocean of knowledge, having collected a few cups of water from the edge, convinced we understand the sea. But the real ocean, the deep ocean that covers most of our world and contains most of life, remains as mysterious as it was to the first humans who gazed out at the endless blue horizon and wondered what lay beyond the edge of sight. The mysteries waiting in the darkness below could reshape our understanding of life, change how we see our planet's future, and provide solutions to challenges we haven't even recognized yet. But they'll remain mysteries until we find the courage, the resources, and the wisdom to explore the alien world that lies beneath the waves, right here on our own planet. The ocean's influence on our daily lives operates through mechanisms so subtle and complex that we rarely notice them. Yet they shape everything from the weather outside your window to the very air you're breathing right now. Consider the moisture in the atmosphere around you at this very moment. Much of it began its journey in some distant part of the ocean, evaporated from the surface by solar energy, carried by wind systems we barely understand, and delivered to your location through atmospheric rivers that dwarf the Amazon in their flow of water. These atmospheric rivers are invisible highways of moisture that snake through the sky, carrying water vapor from tropical oceans to distant continents. A single atmospheric river can transport 15 times more water than the Mississippi River, yet most people have never heard of them. They determine whether California experiences drought or flooding, whether Europe enjoys mild winters or faces severe cold snaps, whether monsoons arrive on time in Asia or fail catastrophically. But our ability to predict these atmospheric rivers, to understand where they'll form and where they'll deliver their moisture, it depends on our knowledge of ocean surface temperatures and currents. And here's where our ocean ignorance becomes directly relevant to your daily life. We're trying to predict weather systems that span the globe using ocean data that covers less than 1% of the surface with any real detail. The ocean absorbs and releases heat on scales that make terrestrial weather systems look like gentle breezes. When ocean temperatures shift by even a degree or two over large areas, the effects ripple through the entire global climate system. The El Niño and La Niña patterns, which influence weather across the Pacific and beyond, are driven by changes in ocean temperatures that we can observe but still struggle to predict more than a few months in advance. But El Niño and La Niña are just the most visible examples of ocean atmosphere interactions. There are similar patterns in every ocean basin, some operating on cycles of years, others on decades, and some on timescales so long that we've only recently begun to recognize them. The Atlantic multidecadal oscillation influences hurricane activity, European weather, and African rainfall on cycles of roughly 60 to 70 years. The Pacific decadal oscillation affects marine ecosystems and weather patterns across the entire Pacific Rim on similar timescales. These long-term ocean cycles are particularly important because they determine the background conditions against which shorter-term weather patterns operate. A hurricane season that would be considered normal during one phase of the Atlantic cycle might be catastrophically active during another phase. Drought conditions that might last months as during one Pacific cycle could persist for years during another. Yet our understanding of these cycles is based on little more than a century of detailed observations, and often much less. We're trying to understand patterns that operate on 60-year cycles using data that barely covers 2 complete cycles. It's like trying to understand the plot of a novel by reading random paragraphs scattered throughout the book. The deep ocean's role in these cycles remains particularly mysterious. We know that change in deep water formation and circulation can influence surface patterns, but the connections operate on such long timescales that cause and effect become nearly impossible to untangle. Deep water formed in the Arctic today might not affect tropical surface temperatures for decades, creating delays in the climate system that make prediction extraordinarily difficult. This temporal complexity extends to ocean ecosystems as well. Many marine organisms have life cycles that span multiple years or even decades, linking their populations to ocean conditions that existed long before current environmental stresses began. A fish population that appears stable today might actually be responding to ocean conditions from 5 or 10 years ago, while current conditions are already determining the health of populations we won't see the effects of until the future. The Antarctic Ocean presents perhaps the most dramatic example of our limited understanding creating potentially catastrophic blind spots in our knowledge. The waters around Antarctica drive global ocean circulation, produce much of the deep water that flows through all ocean basins, and store vast quantities of carbon dioxide in forms we're only beginning to understand. But the Antarctic Ocean is also one of the most difficult places on Earth to study. Ice cover limits access for much of the year. Storms create some of the most dangerous conditions any research vessel can encounter, and the remoteness means that equipment failures or emergencies can become life threatening situations with no possibility of immediate rescue. Despite these challenges, what little we do know about the Antarctic Ocean suggests it's changing rapidly. Ice shelves are melting from below, warmed by deep ocean currents that have shifted in ways we didn't predict. The formation of deep water, a process that has remained stable for thousands of years, shows signs of slowing or shifting location. These changes could fundamentally alter global ocean circulation, but we lack the observational network to understand what's happening or predict what might happen next. The complexity becomes even more daunting when we consider that the Antarctic ice sheet contains enough water to raise global sea levels by nearly 60 meters if it were to melt completely. Even partial melting could displace hundreds of millions of people and reshape coastlines around the world. The stability of this ice sheet depends partly on the temperature of the deep ocean water that flows beneath the floating ice shelves. Yet we have temperature measurements from only a handful of locations around the entire Antarctic continent. We're essentially trying to predict the future of global sea levels using thermometer readings that would barely be adequate for monitoring the temperature in a single room. The consequences of being wrong aren't just academic, they involve the displacement of entire populations, the loss of major cities, and economic disruption on a scale that has no precedent in human history. The Arctic Ocean presents similar challenges with equally global implications. Arctic sea ice has been declining rapidly, creating feedback loops that accelerate warming not just in the Arctic, but globally. As reflective white ice disappears, it's replaced by dark ocean water that absorbs solar energy rather than reflecting it back to space. This absorbed energy warms the Arctic Ocean, which melts more ice, which exposes more dark water in a self reinforcing cycle that appears to be accelerating. But the Arctic Ocean is also changing in ways that aren't visible from satellites or surface observations. The deep Arctic Ocean, long isolated by a layer of cold, fresh water at the surface, is warming as Atlantic water penetrates farther north than it has in recorded history. This warm water doesn't just melt ice from above, It melts it from below, destabilizing ice formations in ways that surface warming alone cannot explain. The implications extend far beyond the Arctic itself. Arctic warming is changing jet stream patterns, the high altitude rivers of air that determine weather across the northern hemisphere. A more meandering jet stream can lock weather patterns in place for extended periods, creating the kind of persistent heat waves, droughts, and cold snaps that stress infrastructure and agricultural systems designed for more variable but less extreme conditions. Yet our ability to predict these changes remains limited by our fundamental lack of understanding of how Arctic Ocean circulation works and how it connects to global patterns. We're seeing the effects of changes we can't fully explain, driven by processes we can't adequately monitor, with consequences we can't accurately predict. The challenge of ocean prediction becomes even more complex when we consider that human activities are changing ocean chemistry in ways that have no precedent in Earth's recent history. The absorption of carbon dioxide is making seawater more acidic at a rate that appears to be unprecedented in at least the last 300 million years. This acidification affects the ability of many marine organisms to build shells and skeletons, potentially disrupting food chains in ways we're only beginning to understand. But ocean acidification isn't uniform across the globe. Different ocean regions are acidifying at different rates, depending on local conditions, circulation patterns, and the types of organisms present. Some areas might be more resilient to acidification, while others might face catastrophic changes to their marine ecosystems. Understanding these regional differences requires detailed knowledge of ocean chemistry, biology, and circulation that we simply don't possess for most of the ocean. The situation becomes even more complex when we consider that ocean acidification interacts with other changes happening simultaneously. Rising temperatures, changing circulation patterns, shifts in nutrient availability, and pollution from land based sources all affect marine ecosystems in ways that might amplify or moderate the effects of acidification. These interactions operate on scales from individual organisms to entire ocean basins and on timescales from days to decades. A coral reef stressed by warming water might be more vulnerable to acidification. A fish population affected by changing currents might be less able to adapt to changing chemistry. An ecosystem disrupted by pollution might lose the species most capable of buffering against acidification. Understanding these complex interactions requires not just more data, but fundamentally different approaches to studying ocean systems. Traditional oceanography has often focused on single variables or processes, studying temperature or chemistry or biology in isolation. But the real ocean operates as an integrated system where everything affects everything else, often with delays and feedbacks that make simple cause and effect relationships nearly impossible to identify. The technological challenges of studying these integrated systems are immense. We need instruments that can measure multiple variables simultaneously, platforms that can operate in harsh conditions for extended periods, and data analysis techniques that can handle the complexity of systems where small changes can cascade into large effects. Recent advances in ocean technology are beginning to address some of these challenges. Arrays of autonomous sensors can now monitor ocean conditions continuously, providing the kind of long term, high resolution data that was impossible to collect just a few decades ago. Sophisticated computer models can simulate ocean processes with increasing realism, allowing researchers to test hypotheses and explore scenarios that would be impossible to study experimentally. But even these advances highlight how much we still don't know. High resolution data from a few locations often reveals variability and complexity that makes it clear how inadequate our sparse global measurements really are. Sophisticated models are only as good as our understanding of the processes they simulate, and they consistently reveal gaps in our knowledge that limit their predictive power. The deep ocean continues to surprise researchers with discoveries that challenge fundamental assumptions about how marine systems work. Recent expeditions have found active ecosystems in places that were thought to be biological deserts, discovered new types of organisms that don't fit existing classifications, and identified processes that weren't included in our models of how the ocean functions. Each of these discoveries is exciting from a scientific perspective, but they also highlight how much our current understanding might be wrong. If we're still discovering new types of ecosystems and new biological processes, how confident can we be in our predictions about how marine systems will respond to continued changes? The economic implications of our ocean ignorance become more pressing as we increasingly turn to the ocean for resources and solutions to land based problems. Offshore wind farms are being built in areas where we have limited understanding of deep ocean currents that could affect their foundations. Aquaculture operations are expanding into deeper waters where we know little about natural productivity cycles or ecosystem resilience. Deep sea mining operations are being planned for seafloor environments that have never been comprehensively studied. These operations will extract metals needed for renewable energy technologies, but they could also destroy ecosystems that took millions of years to develop, and that might contain biological resources we haven't even discovered yet. The irony is profound. In our efforts to develop sustainable technologies to address environmental problems, we might be creating new environmental problems in parts of the planet we don't understand well enough to manage responsibly. We're trading known problems on land for unknown risks in the ocean, a bargain that might seem reasonable if we understood what we were risking, but becomes much more questionable given the extent of our ignorance. The ocean's role as a source of food for billions of people adds another layer of urgency to our knowledge gaps. Global fish catches have been declining for decades despite increased fishing effort, suggesting that many marine populations are being harvested faster than they can reproduce. But our understanding of most fish populations is based on catch data and limited surveys rather than comprehensive population studies. We don't know where most commercial fish species spawn, where their juveniles develop, or how their populations connect across ocean basins. We're managing fisheries based on assumptions about population structure and productivity that might be fundamentally wrong. The consequences of these errors aren't just economic, they involve the food security of coastal communities around the world and the collapse of marine ecosystems that support far more than just the species we harvest. The challenge becomes even more complex when we consider that fish populations are being affected by the same changes that are altering ocean physics and chemistry. Warming waters are causing many species to shift their ranges, following temperature conditions that might be moving faster than the species can adapt. Changing circulation patterns are altering the distribution of nutrients that support the base of marine food chains. These changes mean that historical data about fish populations and productivity might not be reliable guides for future management. We're trying to manage dynamic populations in a changing environment using models based on conditions that might no longer exist. It's like trying to navigate using a map of a city that's being rebuilt while you're trying to find your way through it. The deep ocean's role in all these systems remains largely hidden from our view, yet it likely influences everything from regional weather patterns to global fish populations. Deep currents transport nutrients from polar regions to tropical upwelling zones thousands of kilometers away. Deep water communities process organic matter that affects ocean chemistry on basin wide scales. Deep sea spawning areas for commercial species might be critical to maintaining populations as we harvest in shallow coastal waters. But the deep ocean operates on its own timescales, often much slower than the surface processes we can observe directly. Changes in deep circulation might take decades to affect surface conditions. Deep sea ecosystems might respond to environmental changes years or decades after those changes occur. The deep ocean is like a vast, slow moving flywheel in the Earth's environmental system, storing and releasing energy, nutrients, and biological productivity on timescales that dwarf human attention spans. Our challenge is that we're living through a period of rapid environmental change while depending on systems that operate much more slowly than the changes we're creating. We're pushing on the fast acting parts of the Earth system while remaining largely ignorant of the slow acting parts that ultimately determine how the whole system responds. The ocean's memory is long, and its responses are often delayed. The consequences of what we're doing today might not become apparent for decades, by which time they might be irreversible. We're conducting a grand experiment with systems we don't understand, on timescales longer than human lifespans, with consequences that will affect generations not yet born. This temporal mismatch between human timescales and ocean timescales creates profound challenges for decision making. How do you make policy decisions about activities that might have consequences decades in the future when those consequences involve systems you don't understand in environments you've barely explored? The precautionary principle suggests that when dealing with potentially irreversible changes to poorly understood systems, we should err on the side of caution. But applying precaution to ocean systems would require dramatic changes in how we use marine resources, how we dispose of waste, and how we think about the ocean's role in supporting human civilization. The alternative is to continue our current approach, using the ocean as if we understand it, managing it as if our knowledge were complete, and hoping that our ignorance doesn't lead to catastrophic surprises. But every new discovery from the deep ocean suggests that surprises are inevitable, and that some of them might be far larger and more consequential than anything we've prepared for. The ocean holds secrets that could transform our understanding of life, climate, and the future of our planet. But it also holds the power to transform our world in ways we might not anticipate or be able to control. In the darkness below, Processes are unfolding that will determine the fate of coastal cities, the productivity of marine ecosystems, and the stability of the climate system that has allowed human civilization to flourish. We remain strangers to the ocean that covers most of our world, visitors to the margins of a realm that determines much of our future. Every tide that reaches the shore carries messages from the deep ocean, chemical signals, and biological indicators that could tell us about changes already underway in the darkness below. But we lack the knowledge to read these messages, the instruments to decode these signals, and the wisdom to understand what they might mean for the generations that will inherit the consequences of our choices. The ocean continues its ancient rhythms, indifferent to our ignorance, responsive to forces we can barely measure, evolving in ways we cannot predict. And we continue to live at its edge, dependent on its stability, vulnerable to its changes, and largely unaware of the vast alien world that lies just beneath the surface of the water that surrounds our small, crowded island of dry land. The profound isolation of deep ocean research creates a peculiar kind of scientific loneliness that few other fields of study can match. When a marine biologist descends in a submersible to study life at crushing depths, they enter a realm where human presence is so rare that their arrival might be the first time in millennia that these creatures have encountered anything larger than themselves. The beam of their lights illuminates organisms that have never seen illumination, revealing behaviors that have never been witnessed, capturing moments in evolutionary stories that have been unfolding in complete privacy since long before humans walked the earth. This isolation extends beyond the romantic notion of scientific discovery. It creates practical challenges that fundamentally limit how we can study deep ocean systems. Unlike terrestrial research, where a scientist can return to the same location repeatedly, observe seasonal changes, and build long term studies spanning decades, deep ocean research is often limited to brief, expensive visits separated by years or even decades. Imagine trying to understand the behavior of land animals if you could only observe them for a few hours every 5 years in complete darkness while wearing a bulky protective suit that limited your movement and visibility. This is essentially the situation that deep sea biologists face when studying the creatures that inhabit the majority of our planet's living space. The consequences of this observational limitation are profound. Many deep sea species have life cycles that span multiple years or even decades. Some deep sea fish don't reach sexual maturity until they're 20 or 30 years old. Deep sea corals grow so slowly that colonies might live for thousands of years, accumulating centuries of environmental information in their skeletal structures. Understanding these long lived organisms requires observation programs that span human careers, not just individual research grants. Yet the expense and technical challenges of deep ocean access mean that such long term studies are extraordinarily rare. We're trying to understand ecosystems where individual organisms might outlive the entire history of marine biology as a scientific discipline, using research programs that typically last 3 to 5 years. The temporal mismatch becomes even more challenging when we consider reproduction and population dynamics in deep sea species. Many deep sea creatures reproduce infrequently, with some species spawning only once every few years when conditions are exactly right. Others have complex life cycles that involve migrations between different depths or different ocean basins, journeys that might take years to complete and that we've only recently begun to document. Understanding these life cycles is crucial for predicting how deep sea species might respond to environmental changes, but documenting them requires exactly the kind of long term, repeated observations that are most difficult to achieve in the deep ocean. We might observe a spawning event during one research expedition, then return years later to find no trace of the juvenile organisms we expected to see, with no way of knowing whether our timing was wrong, our location was incorrect, or whether some environmental change had disrupted the entire reproductive cycle. The challenge of deep ocean access also creates significant biases in our understanding of marine ecosystems. Most of what we know about deep sea life comes from areas that are relatively accessible to research vessels, locations near major oceanographic institutions, sites that can be reached without crossing dangerous weather systems, and depths that are within the operating limits of available technology. This geographic bias means that our understanding of deep ocean ecosystems is heavily skewed toward certain regions and certain depths. We know far more about the deep Atlantic than the deep Pacific, simply because Atlantic research institutions have had longer to develop deep sea research programs. We know more about the seafloor than about the water column at intermediate depths, because it's easier to find the bottom than to study the three-dimensional structure of deep water ecosystems. These biases become particularly problematic when we try to make global generalizations about deep ocean processes. A phenomenon that appears common in the well-studied North Atlantic might be rare or absent in the poorly studied Central Pacific. An ecosystem type that seems stable based on observations from accessible locations might actually be highly variable or vulnerable in regions we rarely visit. The problem is compounded by the fact that the ocean doesn't respect the boundaries of human accessibility. Deep currents connect the most remote parts of the ocean with the areas we study intensively. An environmental change in an unstudied region might propagate through deep circulation systems to affect the ecosystems we think we understand. Conversely, our activities in well studied areas might have consequences in remote regions that we'll never be able to document. The technological limitations that create these biases are slowly being addressed by advances in autonomous systems and remote sensing, but they're being addressed unevenly. Sophisticated new instruments are often deployed first in the most accessible locations, where they can be easily maintained and where researchers can quickly respond to interesting findings. This means that our most detailed understanding continues to be concentrated in areas that were already well studied, while truly remote regions remain largely unexplored. The deep ocean's role in global biogeochemical cycles presents another dimension of our knowledge limitations that has far reaching implications for understanding planetary processes. The ocean doesn't just store and transport heat, it's also a massive chemical processing system, cycling elements like carbon, nitrogen, and phosphorus through complex biological and physical pathways that operate on scales from microbial metabolism to global circulation. These biogeochemical cycles are fundamental to maintaining the chemical balance that makes Earth habitable. The ocean's ability to absorb carbon dioxide helps regulate atmospheric concentrations of greenhouse gases, The cycling of nutrients through deep and surface waters determines the productivity of marine ecosystems. The transport of oxygen from surface waters to the deep ocean determines which areas can support complex life. But these cycles operate through mechanisms that are extraordinarily difficult to study. Chemical transformations that occur in the deep ocean happen slowly over timescales of years to decades. Biological processes that drive these transformations often involve microorganisms so small and so sparsely distributed that detecting them requires sophisticated techniques that can only be applied to small samples. Understanding how these cycles work requires tracing chemical pathways through three-dimensional ocean systems that span thousands of kilometers and multiple depth zones. It requires understanding how physical processes like mixing and circulation interact with biological processes like photosynthesis and decomposition. It requires knowledge of how these interactions vary with season, location, and environmental conditions. Yet our ability to measure these processes is limited by the same factors that limit all deep ocean research: access, cost, and the technical challenges of making precise measurements in harsh environments. We can measure ocean chemistry at scattered points and times, but we can observe the continuous, three-dimensional chemical processes that determine how the ocean functions as a global system. This limitation becomes critical when we consider that human activities are altering these biogeochemical cycles faster than we can understand them. We're changing the chemical inputs to the ocean through pollution and atmospheric deposition. We're altering the physical conditions that drive circulation and mixing. We're modifying the biological communities that mediate chemical transformations. The consequences of these changes operate on the same long timescales as the cycles themselves. Chemical alterations that begin today might not have their full effects for decades. Biological changes might not become apparent until entire generations of long lived organisms have been replaced. We're conducting a global chemistry experiment with results that might not become clear until long after the opportunity to modify our approach has passed. The deep ocean's microbial communities represent perhaps the most significant gap in our understanding of global biogeochemical cycles. These communities, which might contain more biomass than all terrestrial life combined, mediate most of the chemical transformations that occur in seawater. They determine how efficiently the ocean absorbs carbon dioxide, how quickly organic matter is decomposed, and how nutrients are recycled through marine food webs. But studying these microbial communities requires techniques that are at the cutting edge of molecular biology and biochemistry. The organisms are often impossible to culture in laboratory conditions, making it difficult to study their metabolism and life cycles. They exist in such low concentrations that collecting enough material for analysis requires filtering enormous volumes of seawater. Recent advances in genetic sequencing have revealed that deep ocean microbial communities are far more diverse than anyone suspected. Every water sample contains thousands of species, most of which are completely unknown to science. Each species likely has unique metabolic capabilities, unique responses to environmental conditions, and unique roles in biogeochemical cycles. The diversity is so great that after decades of intensive study, we're still discovering new major groups of microorganisms with metabolic pathways that don't fit existing models of how marine ecosystems function. These discoveries aren't just adding details to our understanding, they're revealing that our fundamental models of ocean chemistry might be incomplete or incorrect. The implications extend far beyond academic biology. Climate models rely on assumptions about how the ocean processes carbon, assumptions that are based on our limited understanding of microbial metabolism. If these assumptions are wrong, our predictions about future atmospheric carbon dioxide levels and climate change could be significantly off target. Ocean productivity models that predict fish populations and marine ecosystem health depend on our understanding of how nutrients are cycled through marine food webs. If we're missing major components of the microbial communities that drive these cycles, our models might be predicting ecosystem responses that bear little resemblance to what actually occurs in nature. The challenge of studying deep ocean microbes is compounded by the fact that their communities change dramatically with depth, location, and season. Microbial communities at the surface are dominated by photosynthetic organisms that depend on sunlight. Communities in the deep ocean are dominated by organisms that derive energy from chemical reactions. Between these extremes lies a complex three-dimensional structure of microbial communities, each adapted to specific combinations of light, temperature, pressure, and chemical conditions. Understanding how these communities are organized requires mapping biological diversity in three dimensions throughout the entire water column, a task that would challenge our technical capabilities even if the ocean were easily accessible. The seasonal and longer term variability of these communities adds another layer of complexity. Microbial communities in the surface ocean change dramatically with the seasons as light levels, temperature, and nutrient availability shift. These changes cascade through the entire water column as organic matter from surface communities sinks to deeper waters, providing food and nutrients for deep sea microbes. But the timescales of these changes vary enormously. Surface communities might respond to seasonal changes within weeks or months. Deep water communities might respond to the same changes with delays of months or years, as organic matter slowly sinks through thousands of meters of water column. Understanding these connections requires sustained observations over multiple years, the kind of long-term study that's most difficult to achieve in deep ocean environments. The deep ocean's role in the global nitrogen cycle presents a particularly striking example of how our limited understanding creates uncertainty about fundamental planetary processes. Nitrogen is essential for all life, but most organisms cannot use the abundant nitrogen gas that makes up most of our atmosphere. They depend on fixed nitrogen, nitrogen that has been converted into chemical forms like ammonia or nitrate that can be incorporated into biological molecules. For most of Earth's history, the availability of fixed nitrogen was thought to limit the productivity of marine ecosystems. Organisms that can fix nitrogen from the atmosphere, converting it into biologically available forms, were considered among the most important species in marine food webs because they provided the foundation for all other biological activity. But recent discoveries in the deep ocean have revealed that our understanding of the nitrogen cycle was incomplete. Deep sea microorganisms have been found that can perform nitrogen fixation in conditions that were thought to make the process impossible. Other deep sea organisms have been discovered that can perform chemical transformations of nitrogen compounds that weren't known to occur in marine environments. These discoveries suggest that the deep ocean might be a much more active participant in the global nitrogen cycle than previously thought. Instead of being primarily a sink for nitrogen compounds produced in surface waters, the deep ocean might be a significant source of fixed nitrogen, contributing to marine productivity through pathways that aren't included in current models. The implications are profound. If the deep ocean is a major source of fixed nitrogen, then our understanding of what limits marine productivity might be fundamentally wrong. Ocean regions that appear to be nitrogen limited based on surface measurements might actually receive significant nitrogen inputs from deep water processes we haven't accounted for. Climate change could alter these deep water nitrogen processes in ways that dramatically affect global marine productivity. Changes in the deep water temperature, chemistry, or circulation could enhance or inhibit nitrogen fixation by deep sea organisms. The results might not become apparent for years or decades, as deep water processes operate on much longer timescales than surface processes. Yet we're making decisions about ocean management and climate policy based on models that might not include these processes at all. We're trying to predict the future of marine ecosystems while remaining ignorant of biogeochemical cycles that might determine their fundamental productivity. The discovery of new nitrogen cycle pathways in the deep ocean is part of a broader pattern of findings that challenge basic assumptions about how marine ecosystems function. Deep sea research consistently reveals processes, organisms, and chemical pathways that weren't predicted by theories based on surface ocean observations. This pattern suggests that our understanding of the ocean might be fundamentally limited by our focus on the accessible surface layers. The deep ocean isn't just a scaled up version of surface processes, it's a different kind of ecosystem entirely, operating according to principles that we're only beginning to discover. The economic value of deep ocean resources remains largely unmeasured and probably unmeasurable, but it's likely enormous. The biological diversity of deep sea environments represents a vast library of genetic information that could revolutionize biotechnology, medicine, and materials science. The mineral resources of the deep sea floor could supply critical materials for renewable energy technologies. The deep ocean's role in climate regulation provides services that are essential for human civilization but impossible to price. Yet we're making decisions about exploiting these resources based on incomplete information about what we might be gaining and what we might be losing. Deep sea mining operations are being planned without comprehensive surveys of the ecosystems they might affect. Biotechnology companies are beginning to explore deep sea organisms without understanding how harvesting might affect the populations or ecosystems involved. The challenge is that the economic value of deep ocean resources operates on different timescales than most economic planning. The biological innovations that could emerge from studying deep sea organisms might take decades to develop into useful technologies. The mineral resources of the deep sea floor might not be essential until land based sources are exhausted. The climate services provided by deep ocean processes might not be fully appreciated until they begin to fail. These temporal mismatches create profound challenges for policy and planning. How do you weigh immediate economic benefits against long term environmental risks when both the benefits and the risks involve systems you don't fully understand? How do you balance the need for resources today against the possibility that those same resources might be critical for solving problems that haven't yet emerged? The deep ocean's contribution to human welfare operates largely through indirect pathways that make its value difficult to recognize and even more difficult to quantify. The deep currents that transport heat around the globe determine regional climates that affect agriculture, energy use, and human settlement patterns. The deep sea ecosystems that process organic matter and cycle nutrients determine the productivity of surface waters that support fisheries and coastal communities. These services are provided automatically and invisibly without human intervention or management, making them easy to take for granted. But they depend on the continued functioning of deep ocean systems that we barely understand and that are being altered by human activities in ways we can't predict. The loss of these services might not become apparent until they begin to fail, by which time the changes might be irreversible. Deep ocean systems operate on such long timescales that damage might accumulate for decades before its effects become visible at the surface. By the time we recognize that something is wrong, the opportunity to prevent more serious problems might have already passed. This creates what economists call a tragedy of the temporal commons, a situation where short term decisions create long term costs that aren't borne by the decision makers. We're making choices about using ocean resources based on immediate needs and observable benefits, while the costs of those choices might not become apparent until future generations inherit the consequences. The deep ocean continues to challenge our most basic assumptions about how planetary systems work, how life can exist, and how human activities interact with natural processes. Every expedition into the depths reveals new complexities, new connections, and new reasons to question what we thought we knew about our own planet. In the crushing darkness below, processes are unfolding that determine the fate of surface ecosystems, climate systems, and ultimately human civilization itself. Yet we remain largely ignorant of these processes, unable to monitor them adequately, and incapable of predicting how they might respond to the changes we're creating. The ocean's mysteries aren't just scientific curiosities. They're gaps in our understanding that could determine whether human civilization can successfully navigate the environmental challenges of the next century. The answers to questions about climate stability, resource availability, and ecosystem resilience lie hidden in the darkness below, waiting for us to develop the technology, dedicate the resources, and find the wisdom to explore the alien world that covers most of our own planet. We stand at the shore of an ocean of ignorance, having barely wet our feet in the shallow waters of surface understanding, while the deep currents of planetary process flow unseen beneath us, carrying the future in their dark embrace. The ocean's secrets could save us or surprise us, but they will remain secrets until we find the courage to venture into the depths and confront the humbling reality that we are still strangers to the world that made us. The ocean's memory extends far beyond what any human civilization has ever witnessed, encoded not just in ice cores or sediment layers, but in the very structure of water masses that have been traveling through the deep for centuries. When water sinks in the polar regions today, it carries with it the chemical signature of our current atmosphere, but it joins currents that contain water from decades and centuries past, creating a flowing archive of Earth's environmental history that we've barely begun to read. These ancient water masses flow through the deep ocean like slow moving rivers, some taking more than 1,000 years to complete their circuit around the globe. They carry within them dissolved gases, nutrients, and chemical tracers that tell stories of atmospheric conditions from times when the world was very different from today. Some of the water flowing past the deepest ocean floor last saw sunlight when medieval civilizations were rising and falling, when the climate was cooler and the atmosphere contained far less carbon dioxide. Understanding these deep currents isn't just a matter of academic curiosity. They represent one of the most important components of Earth's climate system, a vast conveyor belt that distributes heat, nutrients, and dissolved gases throughout the global ocean. When this circulation system changes, the effects ripple through every aspect of the planet's environmental systems, influencing everything from regional weather patterns to the productivity of marine ecosystems thousands of kilometers away. Yet mapping these currents requires techniques so sophisticated and measurements so precise that we've only recently begun to understand their basic structure. Unlike surface currents, which can be observed from satellites or tracked with floating instruments, deep currents are invisible from above and move so slowly that detecting their flow requires instruments sensitive enough to measure movements of centimeters per second. The instruments themselves must be designed to operate in conditions that would destroy most human made devices. They must withstand crushing pressure, corrosive seawater, and temperatures just above freezing, all while maintaining the precision necessary to detect subtle changes in water properties that reveal current patterns. Many of these instruments are deployed for months or years at a time, collecting data in complete isolation before they can be recovered and their information analyzed. When researchers do manage to map these deep currents, they often discover patterns that challenge fundamental assumptions about how the ocean works. Currents that were thought to flow in one direction are found to reverse seasonally. Water masses that were believed to remain separate for centuries are found to mix in unexpected locations. Circulation patterns that climate models assumed were stable are revealed to be highly variable, changing in response to atmospheric conditions or other ocean processes in ways that weren't predicted. These discoveries highlight a troubling reality. We're building our understanding of climate change on models that may not accurately represent one of the most important components of the climate system. The ocean's deep circulation affects everything from the rate at which carbon dioxide is absorbed from the atmosphere to the distribution of nutrients that support marine life. If our models don't correctly capture how this circulation works, our predictions about future climate conditions could be seriously flawed. The challenge becomes even more daunting when we consider that deep ocean circulation appears to be changing in response to human activities. The warming of surface waters, the melting of polar ice, and changes in precipitation patterns are all affecting the formation of deep water masses in ways that could fundamentally alter global circulation patterns. In the North Atlantic, where much of the world's deep water is formed, Researchers have detected signs that this crucial process may be slowing down. The sinking of cold, dense water that drives much of the global circulation system depends on precise conditions of temperature, salinity, and atmospheric pressure. As the Arctic warms and ice melts, these conditions are shifting in ways that could reduce or even shut down the formation of deep water. The implications of such a change would be global and profound. The deep circulation system that currently carries warm water northward in the Atlantic, moderating European climates, could weaken or shut down entirely. This would not only cool Europe dramatically, but would also affect rainfall patterns in Africa, hurricane activity in the Caribbean, and marine productivity throughout the Atlantic basin. Similar changes may be occurring in the Southern Ocean around Antarctica, where the formation of deep water masses drives circulation patterns that affect every ocean basin. The warming and freshening of surface waters around Antarctica appears to be altering the characteristics of newly formed deep water, potentially changing circulation patterns that have remained stable for thousands of years. But detecting and understanding these changes requires observational networks that can monitor vast ocean regions continuously over many years. The timescales involved are so long that detecting trends requires decades of consistent measurements. The spatial scales are so large that understanding the patterns requires simultaneous observations from multiple ocean basins. Building such observational networks presents challenges that dwarf most scientific endeavors. The instruments must be incredibly reliable, capable of operating unattended in harsh conditions for years at a time. The data they collect must be transmitted across thousands of kilometers of ocean, often through communication systems that are limited by the physical properties of seawater. The analysis of the resulting datasets requires computational resources and statistical techniques that push the boundaries of current capabilities. Even with these challenges, oceanographers have made remarkable progress in recent decades. International collaborations have deployed networks of instruments that provide unprecedented views of deep ocean circulation. Sophisticated computer models can now simulate global circulation patterns with increasing realism. Advanced statistical techniques can extract signals of climate change from the noise of natural variability. Yet every advance in our observational capabilities reveals new complexities and new uncertainties. High resolution measurements show that deep ocean circulation is far more variable and complex than previous observations suggested. Sophisticated models reveal that small changes in poorly understood processes can have large effects on global circulation patterns. Advanced analysis techniques show that the signals of climate change in deep ocean data are often mixed with natural variations that operate on timescales longer than human observations. The deep ocean's role in storing and releasing heat presents another dimension of complexity that affects global climate in ways we're only beginning to understand. The ocean contains more than 1,000 times more heat than the atmosphere, stored primarily in the deep waters that cover most of the planet. Small changes in how this heat is distributed or released can have enormous effects on global temperature patterns. When surface waters warm due to increased greenhouse gas concentrations, some of that heat is mixed downward into deeper layers, where it can remain for decades or centuries before returning to the surface. This process helps moderate the rate of surface warming, but it also means that the climate system has a kind of thermal inertia that delays the full effects of greenhouse gas increases. Understanding this thermal inertia is crucial for predicting future climate change, but it requires knowledge of mixing processes that operate throughout the entire depth of the ocean. Heat doesn't just move downward from the surface, it's redistributed by complex three-dimensional circulation patterns that involve interactions between different water masses, topographic features on the seafloor, and atmospheric forcing at the surface. These mixing processes are among the most difficult aspects of ocean circulation to observe and understand. They involve turbulent motions on scales from centimeters to hundreds of kilometers, operating over timescales from seconds to decades. They're influenced by everything from wind patterns at the surface to the detailed shape of underwater mountain ranges. The challenge of understanding ocean mixing is compounded by the fact that it varies dramatically in different parts of the ocean. Some regions have vigorous mixing that rapidly exchanges heat and other properties between surface and deep waters. Other regions have very stable layering that prevents vertical exchange for years or decades. Climate models must represent these mixing processes accurately to predict how heat will be distributed in a changing climate. But the observations needed to understand mixing are extraordinarily difficult to obtain. Measuring turbulence in the deep ocean requires specialized instruments that can detect tiny variations in temperature and velocity while being tossed about by the very motions they're trying to measure. The biological components of deep ocean systems add yet another layer of complexity to our understanding challenges. The deep ocean isn't just a physical and chemical system, it's also home to ecosystems that play important roles in global nutrient cycles and carbon storage. These ecosystems affect ocean chemistry in ways that can influence climate, but they operate according to biological principles that are often very different from those governing surface ecosystems. Deep sea organisms face challenges that have led to evolutionary solutions unlike anything found on land or in shallow water. Many deep sea creatures have extremely slow metabolisms, allowing them to survive in environments where food is scarce and intermittent. Some can remain dormant for months or years during periods when no food is available, essentially shutting down their life processes until conditions improve. These slow life cycles mean that deep sea ecosystems respond to environmental changes much more slowly than surface ecosystems. A disturbance that might cause rapid changes in a surface community might not have visible effects in a deep sea community for years or decades. Conversely, environmental changes that occurred years ago might still be working their way through deep sea food webs, causing effects that won't become apparent until the future. This temporal complexity makes it extremely difficult to predict how deep sea ecosystems will respond to ongoing environmental changes. The organisms living there today might be responding to conditions that existed years ago, while current conditions are already determining the future state of ecosystems in ways that won't be visible until much later. The migration patterns of deep sea organisms add another dimension to this complexity. Many species move vertically through the water column on daily cycles, following food sources or avoiding predators. Others migrate horizontally across ocean basins, following currents or seasonal changes in food availability. These migrations connect different parts of the ocean system in ways that are largely invisible from surface observations. An organism that feeds in deep water during the day might transport nutrients to surface waters at night. A species that spawns in one ocean basin might spend its adult life in completely different waters thousands of kilometers away. Understanding these connections requires tracking individual organisms through their life cycles, a challenging task even for surface species, and extraordinarily difficult for deep sea creatures that spend their lives in inaccessible environments. The technologies needed to track deep sea migrations are only now being developed, and the results often reveal patterns that weren't predicted by theories based on surface observations. The discovery that many deep sea species have much larger ranges than expected has a profound implications for understanding marine biodiversity and ecosystem function. Species that were thought to be endemic to specific locations are often found to have populations spread across entire ocean basins. Ecosystems that appeared to be isolated are often connected by species that migrate between them. These connections mean that environmental changes in one part of the ocean can affect ecosystems in distant regions through pathways that are largely unknown. Pollution, habitat destruction, or climate change in one area might have cascading effects that spread through migration networks to affect species and ecosystems thousands of kilometers away. The deep ocean's role in carbon storage represents perhaps the most critical gap in our understanding of how the Earth system will respond to continued greenhouse gas emissions. The ocean already stores roughly 50 times more carbon than the atmosphere, most of it in deep waters and seafloor sediments. Small changes in how this carbon is stored or released could dramatically affect atmospheric carbon dioxide concentrations and global climate. Carbon enters the deep ocean through several pathways, each operating on different timescales and each vulnerable to different environmental changes. Organic matter produced by photosynthesis in surface waters sinks into the deep ocean, where it's slowly decomposed by bacteria and other organisms. Carbon dioxide absorbed from the atmosphere is transported to depth by deep circulation. Calcium carbonate shells and skeletons produced by marine organisms sink to the seafloor, where they may be dissolved or buried in sediments. Each of these pathways involves complex interactions between physical, chemical, and biological processes. The sinking of organic matter depends on the types of organisms producing it, the temperature and chemistry of the water column, and the presence of bacteria and other decomposers. The transport of dissolved carbon depends on circulation patterns that are affected by climate change. The fate of calcium carbonate depends on ocean chemistry that is being altered by the absorption of carbon dioxide from the atmosphere. Understanding how these pathways work and how they might change requires knowledge that spans disciplines from marine biology to physical oceanography to geochemistry. It requires observations that span the entire water column and the seafloor. It requires experiments that can track carbon through complex cycles operating over years to decades. Yet decisions about carbon emissions and climate policy are being made based on models that include simplified representations of these processes, often based on limited observations from a few well-studied locations. The uncertainty in our understanding of ocean carbon storage represents one of the largest sources of uncertainty in climate predictions, yet it's also one of the most difficult to reduce through additional research. The deep sea floor represents another frontier of discovery that could fundamentally change our understanding of planetary processes. Far from being a barren desert, the seafloor is now known to host diverse ecosystems, active geology, and chemical processes that affect ocean chemistry on global scales. Hydrothermal vents, cold seeps, seamounts, and abyssal plains each support unique communities of organisms adapted to extreme conditions. These ecosystems process large amounts of organic matter, cycle nutrients, and produce chemical compounds that affect water chemistry throughout the ocean. They also represent some of the most stable environments on Earth, providing refuges for species during past climate changes and potentially serving similar roles during current environmental changes. But the seafloor is also becoming a target for resource extraction as land based resources become scarce. Deep sea mining operations are being planned that could extract minerals needed for renewable energy technologies, but could also destroy ecosystems that have taken millions of years to develop and that we've barely begun to study. The challenge is that we're making decisions about using seafloor resources without adequate knowledge of what might be lost. Each mining site might be home to species found nowhere else on Earth. Each operation might disrupt chemical processes that affect ocean function on basin wide scales. The sediment clouds created by mining could affect ecosystems hundreds of kilometers away. Yet the regulatory frameworks for managing deep sea mining are based on environmental assessments that can only sample tiny fractions of the areas that might be affected. The timescales of environmental impact studies are measured in months or years, while the ecosystems they're trying to assess operate on timescales of decades to centuries. This mismatch between the pace of development and the pace of understanding creates profound ethical and practical challenges. How do we balance the immediate need for mineral resources against the long term value of ecosystems we don't fully understand? How do we make decisions about irreversible changes to environments that might contain solutions to problems we haven't yet recognized? The deep ocean continues to humble human understanding, revealing complexities that challenge our most sophisticated theories and technologies. Each expedition into the depths uncovers new phenomena that expand our sense of what's possible in the natural world. Each long term study reveals variations and changes that weren't predicted by short term observations. Each new measurement technique shows that processes we thought we understood are actually far more complex than we realized. In the vast darkness below, currents carry ancient water masses on journeys that span centuries. Organisms pursue life strategies that seem to defy the rules of biology. Chemical cycles process elements on scales that affect the entire planet. And through it all, human activities are creating changes whose consequences we can't predict because we don't yet understand the systems we're changing. The ocean's mysteries aren't just gaps in scientific knowledge, they're fundamental limitations in our understanding of the planet that sustains us. Every decision we make about climate, resources, and environmental protection is made in the context of this vast ignorance, this humbling reminder that we remain newcomers to a world whose deepest secrets lie hidden beneath miles of dark water. The abyss gazes back at us with the accumulated wisdom of billions of years, holding answers to questions we haven't yet learned to ask, solutions to problems we haven't yet recognized, and warnings about consequences we haven't yet imagined. In the crushing darkness below, the future of our planet unfolds according to principles we've barely begun to comprehend in a realm that remains as alien and mysterious as the day the first humans wondered what lay beyond the horizon. The ocean's soundscape represents another hidden dimension of deep sea mystery that challenges our understanding of how marine life communicates, navigates, and survives in the perpetual darkness. Sound travels far more efficiently through water than through air, and in the deep ocean, where light cannot penetrate, acoustic signals become the primary means of sensing the environment. Yet we've only recently begun to appreciate the complexity and importance of the ocean's sonic environment. The deep sea is not the silent world that early oceanographers imagined. It resonates with a constant symphony of sounds. The clicks and calls of marine mammals, the crackling of snapping shrimp, the low frequency rumbles of geological activity, and the subtle acoustic signatures of countless creatures we've never seen. These sounds carry information across vast distances, creating communication networks that span entire ocean basins. Whales produce some of the most remarkable sounds in this underwater orchestra. Blue whales, the largest animals ever known to have existed, communicate with calls so low in frequency that they can travel for thousands of kilometers through deep ocean sound channels. These calls are below the range of human hearing, infrasonic communications that allow individual whales to maintain contact across distances that would separate them beyond any possibility of visual contact. The discovery of these long distance whale communications revealed something extraordinary about ocean acoustics. The deep ocean contains natural sound channels, layers of water with specific temperature and salinity characteristics that act like underwater waveguides, focusing and directing sound waves across enormous distances. These sound channels, known as SOFAR channels, allow acoustic signals to travel much farther than they could in a uniform ocean. But human activities are fundamentally altering the ocean's acoustic environment in ways that could disrupt communication systems that have evolved over millions of years. Ship traffic creates continuous low-frequency noise that can mask whale calls across entire ocean basins. Seismic surveys for oil exploration produce some of the loudest sounds in the ocean, acoustic pulses so intense they can be detected thousands of kilometers away. The cumulative effect of human-generated ocean noise has increased dramatically over the past century, coinciding with the expansion of global shipping and industrial activity. Background noise levels in many parts of the ocean have increased by orders of magnitude, creating an acoustic fog that may be preventing marine animals from communicating effectively. The implications of this acoustic pollution are only beginning to be understood. Marine mammals that depend on sound for navigation, feeding, and reproduction may be suffering from the equivalent of hearing loss on a global scale. Deep sea creatures that use sound to locate prey or avoid predators may be struggling to survive in an increasingly noisy ocean. Yet studying the effects of noise pollution on deep sea life presents the same challenges that limit all deep ocean research. The animals most likely to be affected live in environments we can rarely access. Their behaviors and communication patterns occur on timescales that are difficult to observe with brief research expeditions. The acoustic environment itself is complex and variable, making it difficult to separate the effects of human noise from natural variations. Recent technological advances have begun to provide new insights into the ocean's acoustic environment. Networks of underwater microphones can monitor ocean sounds continuously, revealing patterns of biological activity that would be impossible to detect through visual observations alone. Sophisticated analysis techniques can identify the acoustic signatures of different species, track their movements, and monitor their behavior remotely. These acoustic monitoring systems have revealed that the deep ocean is far more acoustically active than anyone suspected. Every depth zone has its own characteristic soundscape, dominated by different types of organisms producing different kinds of sounds. The deep scattering layer that migrates vertically each day creates a moving wall of acoustic activity as billions of small creatures move through the water column. But perhaps most remarkably, acoustic monitoring has revealed that many deep sea creatures produce sounds that serve functions we're only beginning to understand. Deep sea fish that were thought to be solitary and silent have been found to produce complex acoustic signals that may serve as mating calls, territorial markers, or feeding coordination signals. The bioluminescent displays that many deep sea creatures produce may be accompanied by acoustic signals that we've never detected because we lacked the technology to listen for them. The chemical communications that occur between deep sea organisms may be supplemented by acoustic cues that help coordinate complex behaviors in the darkness. Understanding these acoustic ecosystems requires technology that can operate in the extreme conditions of the deep ocean while maintaining the sensitivity needed to detect subtle acoustic signals. The instruments must be able to distinguish between biological sounds and the noise created by geological activity, ocean currents, as in human activities. The challenge becomes even more complex when we consider that acoustic signals in the deep ocean are affected by the same physical processes that make deep sea research difficult in general. Sound transmission varies with temperature, salinity, and pressure in ways that can dramatically alter how far acoustic signals travel and how clearly they can be received. Ocean currents can bend sound waves, creating acoustic shadows where signals cannot penetrate, and acoustic focusing zones where sounds become amplified. Underwater topography can reflect, scatter, and absorb acoustic energy in complex ways that depend on the frequency of the sounds and the detailed structure of the seafloor. These acoustic complexities mean that interpreting the sounds we detect from deep sea environments requires understanding not just the biology of the organisms producing them, but also the physics of sound transmission through complex, three-dimensional ocean environments. The deep ocean's geological activity contributes another layer to this acoustic complexity. The seafloor is not a static surface, but an active geological environment where tectonic plates meet, volcanoes erupt, and earthquakes occur. These geological processes produce acoustic signals that can be detected throughout the ocean, but distinguishing between geological and biological sounds requires expertise in both oceanography and seismology. Hooks, underwater volcanic eruptions, can produce sound pulses so intense they can be detected on the opposite side of the planet. Tectonic activity along mid ocean ridges creates continuous low frequency rumbling that forms part of the ocean's background noise. Underwater landslides and avalanches produce acoustic signatures that may be confused with biological sounds unless researchers understand the geological context. The interaction between geological and biological acoustic environments adds yet another dimension to the mystery of deep ocean ecosystems. Some deep sea creatures may use geological sounds as navigation cues, orienting themselves relative to known sources of acoustic activity. Others may have evolved to avoid areas where geological noise would interfere with their own acoustic communications. Understanding these interactions requires interdisciplinary approaches that combine biology, physics, geology, and engineering expertise. It requires long term monitoring programs that can track both biological and geological acoustic activity over multiple years. It requires sophisticated analysis techniques that can separate different types of acoustic signals and identify their sources. The ocean's acoustic environment also varies dramatically with season, weather, and longer term climate patterns. Storm activity at the surface creates noise that penetrates into the deep ocean, potentially affecting deep sea acoustic communications. Seasonal changes in ice cover alter the acoustic properties of polar waters. Long term changes in ocean temperature and circulation affect sound transmission characteristics throughout the water column. These variations mean that the acoustic environment experienced by deep sea organisms is constantly changing, creating challenges for species that depend on acoustic cues for survival. Climate change may be altering acoustic conditions in ways that affect deep sea ecosystems, but detecting these changes requires baseline measurements that we're only now beginning to collect. The potential for using acoustic monitoring to study deep sea ecosystems represents one of the most promising frontiers in ocean research. Unlike visual observations, which require expensive submersibles and provide only brief glimpses of deep sea life, acoustic monitoring can operate continuously, providing long term records of biological activity throughout the water column. Acoustic techniques could potentially allow researchers to monitor deep sea ecosystems remotely, tracking changes in species composition, behavior, and population dynamics without the expense and logistical challenges of direct observation. They could provide early warning systems for environmental changes, detecting shifts in ecosystem function before they become apparent through other means. But realizing this potential requires developing acoustic monitoring networks that can operate in the harsh conditions of the deep ocean while providing the sensitivity and reliability needed for long term ecosystem monitoring. It requires building databases of acoustic signatures that can identify different species and behaviors. It requires analysis techniques that can extract meaningful ecological information from complex acoustic datasets. The deep ocean's acoustic mysteries extend beyond the sounds produced by known organisms to include acoustic phenomena that we can detect but cannot yet explain. Deep sea monitoring systems regularly record acoustic signals that don't match any known biological or geological sources. These mystery sounds may be produced by species we haven't discovered, by behaviors we haven't observed, or by physical processes we don't understand. Some of these unidentified sounds occur regularly, suggesting they're produced by biological processes, but their characteristics don't match the acoustic signatures of any known deep sea species. Others occur sporadically, sometimes in patterns that suggest their responses to environmental conditions, but their sources remain unknown. The investigation of these mystery sounds requires the same patient, long term approach that characterizes all deep sea research. Identifying their sources may require correlating acoustic records with direct observations, tracking their occurrence across different locations and depths, and developing new theoretical models for how deep sea organisms might produce and use acoustic signals. The ocean's acoustic environment also provides a unique window into the past, preserving records of environmental conditions and biological activity that extend far beyond the reach of other observational techniques. Ice sheets record atmospheric conditions going back hundreds of thousands of years, but acoustic recordings can potentially document ocean conditions on much shorter timescales with much higher temporal resolution. Long term acoustic monitoring stations could provide detailed records of how deep sea ecosystems respond to environmental changes, how species composition shifts over time, and how human activities affect marine life. These records could become invaluable for understanding natural variability in ocean systems and for detecting the effects of climate change and other human impacts. And so we return to the surface, having glimpsed the vastness that lies beneath. The ocean spreads endlessly around us, its dark waters holding secrets that could reshape everything we think we know about life, climate, and our planet's future. We've explored less than 5% of this realm, yet even that tiny fraction has revealed wonders that challenge our understanding of what's possible. In the crushing depths below, ancient currents carry water that last saw sunlight when civilizations were rising and falling, while creatures beyond our imagination solve problems we've never considered, using strategies evolution has perfected over millions of years. The ocean remains Earth's greatest mystery, a frontier more alien than Mars, yet more crucial to our survival than the air we breathe. Until we find the courage to truly explore this underwater universe, we'll remain strangers to the very world that made us, standing at the edge of an endless blue horizon, wondering what lies beyond the reach of light.